my topic today, I hope by the end of today, we will all agree that design has a very big role in meeting those sustainable development goals. My overall topic, engineering our future, and the role of life cycle design and systems thinking in that. We've just seen that. What I want to do is start with a very broad overview of a view of our engineered world, considering the world as material flows. Yesterday in the Product Service Systems Day, we heard about the Ellen MacArthur Foundation in the UK and its work in the circular economy. I'm going to use a diagram from that Ellen MacArthur Foundation, but in which I leave off the circular bit, but say that the economic activities that we have essentially deal with material flows from sources to sinks. We grow things, we hunt them, we fish them, we dig them out of the ground, we pump them out of the ground. Both biological materials and technical materials. We process them. We form them into products. We transport those products around and sell them. We consume them. We use them. And at the end of that, there are some resulting waste materials. Perhaps we can recover some energy from the materials by combustion or by digestion. But much of the result ends up in the biosphere, in landfill, in watercourses, in the atmosphere. That's what our industrial society does. And it's driven by energy. And much of that energy is dug out of the ground or pumped out of the ground. And much of that energy leads to emissions which go into the atmosphere at the end. Now, some of that material remains in use for many years. Infrastructure, we have 10 tons of steel for every man, woman and child in Europe, more or less, which we use in our infrastructure and so on. But at each end of the flows that we have constraints. At the source end, we are meeting diminishing returns everywhere. In the 19th century, we could find copper as great nuggets in watercourses. At that time in the 19th century, most of the tin and copper in the world came from southwest of England, near where I live. And at that time, ores were 10% copper. The lower left picture is Bigham Canyon in Utah, the biggest hole in the world, man-made, a kilometer deep. And that, in the last century, had 2% copper ores. Now we're down to about 1% and diminishing. And in order to deal with that 1%, we need energy. And we have the same in oil. We've heard that we keep finding more oil, but we have diminishing returns on the ease of getting that oil. I've heard it said, it's a rather crude analogy, that having conventional oils is like having a beer from the tap in a bar. Having unconventional oils is like sucking the beer out of the carpet on the floor. And that's what we've got down to in tight oils and fracking, and we need enormous energy just to get the energy. And this diagram is from a proceedings of the Royal Society, a special issue on the future of oil a couple of years ago. And the editors at the end of their introduction said, adapting rapidly and peacefully to oil scarcity in a manner that does not destroy the global environment provides humanity with a formidable challenge. If you note there, that was 3 years ago, it was about 93 million barrels a day. Today it's 98, 1.5% increase still. And it's this is the IEA predicting we're going to well over 100. At the other end, at the sinks, we also have issues. The flow of fertilizers into our watercourses leads to algal blooms, eutrophaction. Ozone, other gaseous emissions lead to smogs. We have issues of physical solid material everywhere. We were hearing yesterday about microparticles, microplastic particles in the sea. And of course, lower right is the probably the most famous diagram about our impacts, which is the impacts of future representative concentration pathways of gaseous emissions on irradiation and what the consequences for temperature would be. And if we look at that RCP 2.6, which is what we need to perhaps stay to 1.5, 2 degrees, we need very significant reductions from now, but also, if you look at the end, we need to be able to develop technologies for extracting CO2 from the atmosphere, which are by no means proved, but that's what we're depending on at present. So we have an urgent need for action. These are pictures from the last week from newspapers. The UN News Centre UN sees a worrying gap between Paris climate pledges and emissions cuts. BBC recorded last week a record surge in atmospheric CO2 in 2016. And even for the very easy to access Saudi crude oils, Saudi needs $70 a barrel to break even. So we have an urgent need for action. But we also have very incommensurate worldviews. I can remember Ronald Reagan saying, there is no limit to growth and human progress while men and women are free to follow their dreams. And that's very much the cornucopian view of the world. We need unfettered free markets. We need to prioritize policies to maximize growth. At the other end of the scale, extreme preservationists are saying we need highly regulated deep green economies, reduced scales of economy, even reduced scales of population if we're going to meet the challenges. I'd be interested to know in this room where you are on that scale. How many of you are in the accommodation, perhaps? How many of you are in the communalism category? And whether you've changed category in recent years. Essentially, though, what we have to do is to decide what in the future is going to be the nature of our artificial world. And those in the design community know that that's a design issue. We design the artificial world. Before we can make it, we design it. Now, design is a word that has a difficult background, because for a lot of people, design means aesthetics. Design means how things look. But Steve Jobs tells us that's not right. Design is about how things work. To design something well, you need to know how it works. You've got to get it. And that's the first point to say. If we're to design the world well, we have to understand really well how it works. The second thing is design is about changing things. It's about, this is from Herb Simon, Nobel laureate. Everyone designs who devises courses of action aimed at changing existing situations into preferred ones. And a physician doing a patient plan is designing. A politician doing a bill of state is designing. And engineers design every day. But design is also about synthesis and creation. Design is about pulling things together. Design is about bringing artist and inventor and mechanic, as Buckminster Fuller said. So what's a view of the world from a design point of view? I'm going to present the view that I've come to first and what I think the consequences are for environmental and sustainability issues. First of all, the person who's influenced me very much is a man by the name of W. Brian Arthur, and he wrote a book on the nature of technology. And he said, in our artificial world, we assemble things together from technologies. As we look around the room, glass is a technology. The building materials are technology. The lamps are technologies. The computers are technology. We assemble the world together and adapt those technologies to different needs. We also, what technologies do is that they embody natural phenomena to some useful purpose. But we also all the time identify new natural phenomena, and we have to turn those into useful purpose. So, for example, graphene. How do we make graphene into useful technologies. This picture is from DTU-Nano, which is doing just that just now. So that's the first thing. We assemble the artificial world from technologies. The second, though, is that if we look in any area, we scrabble around in the early days and try different ideas of it until eventually we settle on particular patterns of doing things. And we call them dominant designs. Top left, anyone know what year the Fordson tractor was? 1918. 100 years, tractors have looked the same, essentially. How about the Boeing 7-7 prototype? 54, I think. 65, 63 years. And they still look the same. We still have the same pattern. Bottom left, middle 19th century, Bristol, my home city, that's the Clifton Suspension Bridge. Kobe Suspension Bridge in Japan, still the same principles 160 years later. And the Mini, 1960, still the same principles. So everywhere, the world we have is based on engineered patterns. But more than that, those patterns, many of them were established a long time ago. Ollie DeVeck and colleagues from MIT, their great book, Engineering Systems. 100 years ago, engineers basically worked on getting artifacts right, making cars work, making telephones work, making light bulbs work. In the middle of the last century, they formed those together into systems. The public switch telephone network, the electric power grid, the interstate highway system, and so on. And at the end of the last century, those systems became intertwined with each other into complex engineered systems. The transportation system, the energy system, communication system, healthcare system, manufacturing system, and so on. We have systems of systems, all of things in which we have standard patterns. And those patterns were created on the basis that we had good access to fossil fuels. And we have to design at all scales. Every aspect of a wind farm has got to be designed. Every aspect, not necessarily all at once by the same group, but every aspect has to be designed, down to every aspect of a nano device for sepsis detection has got to be designed. And we have to design every surface, every material, every tolerance. But designers also have to take many viewpoints into account. This is from DeVeck and colleagues again. They said if you go back to the beginning of the last century, what they did was looked at what people were publishing about what they called the illities, the issues that designers were having to deal with. Originally, it was safety, it was quality, it was reliability, it was durability. Would the things work well? Middle of the last century, usability and maintainability. The end of the last century, interoperability. These complex interlinked systems, were they interoperable, but also coming up very rapidly from about 1970, sustainability. So with that background, what are the modes of change that we could see in that would allow us to take these systems of patterns of doing things and change them to be more sustainable? Now, I think we can identify a number of approaches we can use. Just before we do so, I want to just introduce one other term, and this is a term we use as designers, which is the solution principle. That designers propose concepts for how things are going to be done, and those concepts embody solution principle. And a simple example of fridge. A fridge is an insulated box with a pump pumping fluid through a condenser and an evaporator in order to cool the area. That is a solution principle, and fridges everywhere basically use that solution principle. Those are design patterns we reuse. Our wind turbines are in patterns that we generally incrementally develop and reuse. We can hold those principles constant and just change the dimensions of things. In the fridge, we could make the insulation thicker, and in doing so, we reduce the energy loss. We can improve the shape of the passages in the pump and improve its efficiency. But for the The solution principle, which is a car, we can use optimization routines to optimize its weight, its shape for drag, and so on. With remarkable effect, this is the DTU Roadrunner car that achieves about 450 kilometers on a litre of fuel, about 15 times better than the best European cars. And it's essentially a solution principle that we know about. But what we do as well is we substitute within the solution principles. We could take one type of motor in a refrigerator and change it for another. We did at the time of the Montreal Protocol, we take one type of refrigeration fluid, CFC, and substitute another which has a less damaging effect. But here are examples from aircraft. Over 100 years, the solution principle for the wing of an aircraft was spars and ribs, originally in wood, then in riveted sheet aluminium, then in machined from solid aluminium, now in composite. But the solution principle has been unchanged. And these days, the dominant substitution that we do is substituting electric drives, electric actuators, electric motors for internal combustion engines, for example. And I will believe this when I see it, but they're talking about having electric aircraft on at least short haul, Copenhagen to Aalborg perhaps, within a decade or so by substitution. The third principle that we can use is that we can add to the solution principle means of controlling the device better, dealing with adverse effects. So an engine, for example, we add exhaust after treatment and engine control to reduce the gaseous emissions from the engine. Our lighting systems have controls on them such that if the room's not occupied, it switches off, and so on. These are pictures from work that DTU Compute's doing in a sort of smart city area, and if I understand it, they're, for example, controlling water treatment systems such that the treatment is done when the CO2 produced by electrical energy generation is at its lowest, so that we can optimize that. There's a lot of work on smart is to, for example, improve traffic flow in cities by appropriate sensing, and smart homes allow us to modify when our electrical equipment is used again so that we can reduce CO2 content. But that's all adding things to our existing solution principles. We heard a lot of this yesterday. I'm not going to say so much of this today, but we can take the ways that we do things and try to ensure that we get maximum use out of the embodied energy in them by reusing the materials, by extending the life, and so on. And that's what the circular economy is about. We can design for material recovery. This again is the Ellen MacArthur Foundation. We can make sure that we use compatible materials so that end of life, when we mix them all up together, we can separate them easily. We can design so that we can disassemble easily at the end of life. We can have the reverse logistics so that we can collect up parts and use devices easily. We can ensure that things may be maintained rather than thrown away. Replaceable wearing surfaces, modules which are easy to change, standard designs which it can be supplied from anywhere. And the final thing we can do without changing the fundamental principle of what we do is modify the way that we use it. The US in the 1980s, 55-mile-an-hour speed limit to limit the consumption from vehicles. Today, in shipping, slow steaming, extra slow steaming, limits, it uses the same principle of the ship, but by reducing the speed of operation, reduces the environmental impact. In transport, the greatest thing we can do, I believe, is to try to improve load factors. London buses, the load factor is about 15%. Most of the time, you'd be better off sending people around in taxis. But because, of course, it's sized for the peak times of use. This final picture, the the lower right is aircraft on short-haul flights. If you can, instead of letting down in a series of steps, fly and then glide to the end of the runway, you can save really quite significant amounts in the order of a few percent on a short-haul flight. So what's the potential for improvement of all that? Using those sort of techniques, we can perhaps, in good circumstances, achieve 4 or 5 times improvement. The book, Sustainable Materials with Both Eyes Open, Julian Allwood describes in that how we can get double the use of materials for about half the energy. How we could do it, not how we do it though. And the sort of thing he says is that, unfortunately, steel is so cheap, it's cheaper and easier to put more steel than we need into a structure than it is to do the engineering work to optimize the structure, for example. Bottom right there is some colleagues at the University of Manchester in the UK, a project which they call RACER. And what they say is that the automotive industry could, they believe, make really significant improvements in the performance of conventional vehicles, but they don't. I was in the automotive industry 40 years ago. We talked then about 3 litres per 100 kilometres cars. We're not there 40 years later. And we could be, but we don't have the economic incentives to be. But in other areas, 30% of oil use is shipping, aviation, and trucks. And those are much more difficult to improve. Aviation, that's a curve. We're still making improvements in the performance of aircraft, but not at the 3 or 4 times. And we're not going to do it at 3 or 4 times. We're going to make a few percent improvement. I believe the same with ships and trucks as well. So what else can we do? Then we've got to start thinking of novel solution principles. And that's what this afternoon is about, I hope, is to, Chris is nodding, yeah, is to what are the sort of techniques we can use to try and get novel solution principles. And very often that involves taking technologies and combining them in a different way. Top right is, anyone know what the top right is showing? Out of MIT recently. That's a modular floating nuclear power station, combining offshore platform technologies and nuclear. Big interest in that. Bottom left, Elon Musk suggesting that rather than flying people around or using high-speed trains, we send them in pods down tubes in the Hyperloop. Bottom right is underwater energy storage in compressed air. Top left is what's called ultra PRT, personal rapid transport, a sort of hybrid between tracked vehicles and autonomous vehicles. Again, we heard a lot about this yesterday, and I'm not going to concentrate on it, but we can make change by substituting a physical product for a service, or a service for a physical product, but also improving sharing. And a lot of what we see, Lyft, for example, the average occupancy of a car is about 1.4, 1.5. Double that, and for very little extra energy, we get twice the passenger kilometers. But the same with Airbnb. Airbnb gives us extra access to accommodation without building anything. As long as by doing so, we don't make it so cheap to travel that people travel more. Then you get the rebound effect. We can design for behavioral change. We can try and make our artifacts prompt people or give people the information such that they're encouraged to change the way they use them. Simply putting something like that on a light switch, maybe. But the South Koreans have a food waste system, and those using it get sufficient information about their food waste that they've reduced the waste by about 30%. Bottom left is a European community project that management engineering is involved with, which is giving people information about their energy use. But provide people with a good means of separating their food waste. Provide people with infrastructure for cycling. in the right circumstances, it hasn't always worked. In Stevenage in the UK, it didn't work, but in the right circumstances, you can get very significant behavioural change. But there's another very nice thing which is done in design, which is called reframing the problem. We ask the question, how can we have a low-carbon car? Instead, the question should be, how can we get sensible mobility at low energy? We ask the question, how can we heat, as Europeans, we heat our houses to a sort of envelope the whole house at 21, 23 degrees. Why not say, how do we keep people warm? And that's what the Japanese did, low resource availability. Rather than heating buildings, they keep people warm with a Kotatsu body heating system. And interestingly, I saw this was from the same paper. This was a comparison of Japan and Norway. And I'll let you read that for a moment. But the Japanese washed their clothes in cold water at room temperature. But the way that they assisted a bit is that the whole family were presumably not all at once in the same bath water, and then that water is used in the washing machine to at least start the wash off with some warm water. And that would save very considerably on even the best European practice in washing machines. The final point, though, or two final points for change. How am I doing? Oh, okay. We used to have lots of technologies which were naturally low energy. And we moved away from them because fossil fuels allowed us to do things faster and therefore have less people costs, but at the expense of using energy. But can we perhaps revisit them? The lower left picture, we used to grow peaches in Paris and pineapples in the UK, completely passively, by having thick walls around gardens. And those thick walls raised the local temperature 2 or 3 degrees. We still have extensive passive mechanisms for heating, cooling, ventilation of buildings. Go around the Middle East and you see that the wind towers, such that I remember speaking to Saudis a few years ago, how did they survive 40 degrees? And they said they slept under wind towers. But at the top, we can move things around by water with very, very low energy demand, but with quite high people costs. But perhaps we could combine, as they're doing at MIT and in the Netherlands, combine water transport with autonomous vehicles and get very low energy movement of goods. A final point to make about all of the design, there is a design theory comes from colleagues Reich and Subramanian, which is that we have to remember not just the product, but the social context and the institutional context. And if we forget those, then we risk failure. And the example which they give in a paper is there have been many attempts over the years to try and move away from traditional biomass fuel cookers in India, and most of them have failed. And their argument is they've failed because the alternatives don't recognize the social context. Conversely, there's Harish Handy is an entrepreneur. He has a company called Selco, and they've been quite successful in introducing solar energy in rural India, because he has recognized the social context, what people can afford to pay. They pay a little bit a day. But also the institutional context. How could he maintain this? He trained local cycle repairers to maintain and support the equipment that he was using. So some implications of this. First of all, some dangers. If we have an electric car and we save a few €100 a year on that electric car, and we use that to buy a family holiday in Spain, we undo all the benefits of that. If we have improved insulation of our house and we use it to improve the comfort levels, we can undo the benefits. That's the rebound effect. It's well known. And the rebound effect exists everywhere in this. Second thing is that as we get more efficient, it risks continuing the lock-in that we have to unsustainable patterns. I've seen it said that the suburbs are the greatest waste of resources in the history of humanity. And I'm afraid I tend to agree with that. But the other point is, and this is most concern to me, is that a lot of the things that we do add complexity to our artifacts. We add layers of complexity. We add electronic devices to mechanical artifacts that depend on a global supply chain for them to work. Those electronic devices have energy consumption issues, but they also risk resilience issues. We have to add layers of people to help deal with the possibility of cybercrime and so on. And it's well documented that as we add layers and layers of complexity, eventually we get into trouble which we have to unroll. So that's the first point. The second thing is that there is a whole load of things we can do easily with substitution, and there's a whole load that we still can't do easily. Materials manufacture, we still can't well carbon capture, and we're depending on that in some respects. The diesel engine, as I said, is 30% of oil use. And I did some figures, I'm not sure if this is right. A train would have to carry about 200 tons of battery, a British high-speed train, which would increase its weight by about 50%. I think a large container ship would have to carry about 10,000 tons of battery for each day it operated. And that's not going to happen in the short term. And the same with our big trucks and so on. So there's going to be a whole load of technologies that are not going to be available to us in the future. And a third thing is that a lot of our institutional factors, our regulations have grown up. We can improve things by regulation. We, Rose, and all the other regulations are driving environmentalism. But there's a whole load of regulations that we have came out of the fact that we had easy access to fossil fuels. For example, our urban planning regulations. We used to have houses and factories, commercial areas, all mixed up together, and people walked or cycled between them. This is my home city, and the industrial areas are distributed around the city, separated from where people live, and they have to travel by car between them on the assumption they can. But actually, our industry these days is not like it was 30, 40, 50, 60 years ago when these regulations were formed. Two final points, and out of all that, Julian Allwood is at the University of Cambridge. He's the one who was saying, how can we double our material use with half the energy? This is a letter he wrote to Nature last year. And success today is largely associated with derivative measures of increasing gross domestic product, profitability, speed, or salary. But our value systems, and I think this relates to what Mons was saying earlier, our value systems are based on reputation, heritage, journeys, relationships. And we need to expand our dialogue of climate mitigation to reflect those values. And we need to change our habits of energy use. That should be the first priority of climate change. And we're the ones with the big footprint on this side of the Atlantic and the other side of the Atlantic. So that's the first point. And now my final slide. Going back, I said design is about how things work and about doing things better. Three things. If we're going to understand how things work, we have to have very good life cycle analysis capabilities so that we can properly compute the consequences of these actions. The second is that, as I said, we don't just have individual artifacts, we have interconnected systems of artifacts. And we need to deeply understand those systems and how they work and how they interact with the natural world. And the third thing is we need, as I say, design thinking, knowledge of how we might change the world, what are the directions in which we can go, and the courage and will to do so. Now, I'd like to finish with a quote which is some hundreds of years old from Francis of Assisi. Start by doing what's necessary, then do what's possible, and suddenly you're doing the impossible. We're only just starting to do what's necessary, and we haven't even started doing yet what's possible. Thank you very much.
So, taking questions, Chris?
Thank you. I can start. Just in your presentation, you had a slide to present some possible solution.
Yes.
That leads also to your concluding slide. It is the slide where you are talking about circular economy,
yeah.
where you have the green part and the blue part.
Yes.
And we are actually talking a lot about circular economy. But in this slide, I really like the fact that we can show that it is not a good solution, because as it is the part that is energy driven,
yeah.
you show that then we will consume more and more energy. So it is not still a solution.
To me, circular economy is fundamentally about embodied energy and about keeping materials in use for longer. And ideally getting to the point that we, as I said, we have 10 tons of steel per person in Europe, typically. Can we get to the point that we just keep continually reusing those 10 tons of steel? We stop digging more copper out of the ground and continually reuse it. I think that is a fundamental point that we have to get to. But the circular economy doesn't deal with energy issues. And the energy issues, we have to move away from energy systems which depend on digging stuff out of the ground and putting the results into sinks, to energy systems which are basically use infrastructure to take energy from sunlight and wind and so on. And that's what we're going to hear about shortly, I hope. I mean, I think that the circular economy by itself is not a solution. It's a part. If somebody said, which ones of these should we use? All of them. What's the priority? I don't know. And I really don't know what the priority is on which we should use. But does that... Thank
you. Okay. Yeah, thanks very much for your presentation. I was asking myself, are we talking about the right topic? For example, what is the main problem that has led to the situation that we are in? Do we have an economic system that is allowing to do good by doing well, if at the same time you can do better by doing bad? Yeah. So that is one problem, I think. And the other is, I liked your concept of designing. Obviously, we need to design a whole society. So we should move to the next scale and design a way of living, a sustainable way of living, in order to have a goal for our design. That is just a remark on this.
I think I entirely agree with you. I mean, this week's symposium is a product development symposium, an engineering design, and to some extent I deliberately wanted to do it in a neutral sense, but that slide which I showed earlier, these where are we there is an absolutely fundamental choice, and we have incommensurate worldviews. And I mean, I would from engineering, if I asked engineering students that I work with, 80–90% of them are in the technocentric part of that spectrum. But is that correct?
This leads to the statement that we can't afford saving the planet. Right.
Yeah, that is the... We need to watch the time. Yeah.
If there's no more urgent questions, but I think we've got time for one more.
There's one behind you.
If there's a few people with their hands up, so I'd like to take a separate person. Did you have your hand up as well? Did you have your hand up?
Thank you. Thank you for the talk. Very interesting. I was wondering, what's your opinion towards this report from 2010 from NATO, that 40% of air pollution comes solely from cow meat production, just cow. Yeah. And yeah, we talked about designing, trying to influence behavior of users. Yeah. But if you look at all these very amazingly well done advertisement by those great smart corporations only focusing on financial results, like we've probably seen on Tuesday on the Architecture Day. Yeah. The only focus is mostly the finance and how being smart about it, which makes sense. So yeah, what is your thought on this?
Let me finish by sharing with you a thing. I couldn't believe it when I read it recently, but I checked it out, that 3 people cycling have a higher global warming potential than being in a modern European car per kilometre. Why? Because of the impacts of our food system. If they're meat eaters, 3 people cycling are worse than a car. If they're vegetarians, better. If they're vegans, much better. I haven't even talked about the food system. I hope we'll hear a little bit about that in a bit. But fundamentally, all our systems, why can we have 7 billion people on the planet? Because we use enormous amounts of fossil fuel in our food system, and we eat a lot of meat as we've got richer, and there's enormous amounts of methane produced. And I'm going to stop there if I may, because I'm conscious that I need to hand on to my next speaker